Good afternoon. My name is Farah Guerrero. You are listening to the Blue Hour on CiTR 101.9 FM in Vancouver, right here live in studio on the UBC campus, the University of British Columbia, a place where I grew up, have fond memories, and enjoy coming here once a week. The show was relaunched last week. We had our first show after a long hiatus, and it's a wonderful thing to be able to be back in the studio in this gorgeous time of year. And I have an extraordinary guest today, Dr. Michelle Kunimoto, who is beyond. Let's put it this way. I think there are no words to describe how I feel about interviewing Michelle today. So, but first, I want to do a land acknowledgement because we want to acknowledge that we are broadcasting this show from the traditional, ancestral, and unceded territory of the Musqueam people. And as we move through spring here on the West Coast, I have been thinking about the work of a great artist, Susan Point. She's a renowned Musqueam Coast Salish master carver and artist, and frogs are important symbols and motif in many of her works, and it's connected with the coming of spring and seasonal transformation. Now, my guest today is Michelle Kunimoto, Dr. Kunimoto, astrophysicist and assistant professor in the Department of Physics and Astronomy at the University of British Columbia. Michelle's research focuses on exoplanet detection, characterization, demographics, occurrence rates, and astrostatistics. Michelle completed an honors degree in physics right here at UBC. Physics and astronomy, followed also by a PhD in astronomy, and then later worked at MIT as a postdoctoral fellow and postdoctoral associate before returning to UBC as faculty. Now, Michelle studies planets beyond our solar system, and we're going to be talking a lot about that today. And I think there's no way to describe how I feel because for most of my lifetime, and you could argue most of human history, when we look at the night sky, and certainly when I was young, remembering that what I believed we could only understand was what we could understand in our solar system. So, I was a child in elementary school. I remember looking at books and seeing the planets that became very familiar, and of course, our beautiful star sun. But the reality is, in the last 30 years, lot has changed. So the first confirmed exoplanet planet around a sun-like star was announced around the mid-90s. And so we're just a little bit over 30 years now. And since then, we have confirmed NASA and many scientists around the world collaborating together have confirmed many exoplanets in the thousands, as well as many thousands of candidates, which we'll talk about. So within a single human lifetime, astronomy has moved to worlds really beyond our solar system. And that's extraordinary. So welcome, Michelle, to the show. And thank you so much for coming today.
Yeah, thank you so much for having me.
Yeah, so let's talk about, can you define for us the difference between our solar system and what astronomers mean by an exoplanetary system?
Right, so an exoplanet is really a planet that is outside the solar system and going to be orbiting another star that looks a lot like our sun. There's actually some maybe disagreements within our own community about what exactly you have to be in order to be an exoplanet. For example, there are some objects we found that look very much like planets in our own solar system. They're planetary mass objects, but they don't orbit any star at all. So because they're not in a system that looks just like our own, does that make them an exoplanet or some other class of object? So there's a kind of a lot of definition debates that we have, but pretty much most simply, it's going to be like a planet that's outside our solar system.
So when we look up at the night sky with our naked eyes, we can sometimes see planets in our own solar system, right? Like Venus, Mars, Jupiter, orbiting our own star, right? But the stars themselves that you are studying are outside of this solar system entirely. But we're also, with our naked eyes, looking at stars. So it is interesting. We are seeing them and we're not seeing them. But these planets are, right, orbiting those stars, and that's what you're out to find. Am I right?
Right. So if the next time you go out, and I know in Vancouver it can be very overcast and rainy, but if you see the night sky, and you can just think about every single one of those stars probably has a planetary system around it that looks very much like our own. Now, in terms of kind of whether our solar system appears to be an outlier, like how similar the exoplanets we found in terms of their properties compared to the planets in our solar system, this is something we're still trying to understand. Is our solar system unique? Is it particularly rare, or is it a really common outcome of planet formation? So a lot of the planets that we've found so far tend to be a bit closer to their star than many of the planets in our solar system, but that's really a result of kind of the limitations of surveys right now. So the longer we continue to look at the sky, the better we'll have the ability to find other systems that look just like our solar system.
Now, I brought something personal into the studio today, which I quickly showed you. It was a handwritten science question from my older son from 2015, where when he was in potentially grade 3, the question was, how similar to Earth is Kepler 29? And to me, this speaks to something about how quickly exoplanets have really entered the public imagination during what we could call maybe the Kepler era that he was born into. Now, did the Kepler mission fundamentally change not only astronomy, but how ordinary people, even children, imagine the universe?
Yeah, absolutely. And this is one of, I think, the great legacies of the Kepler mission is doing exactly that. So imagine kind of pre-2009, pre-Kepler mission, a lot of the planets that we'd found so far, exoplanets, were all really, really big planets, like Jupiter-sized planets. And many of them, somewhat surprisingly, orbited really close to their stars. Like they orbited within a few days. Now compare that to our solar system. Mercury is our innermost planet, and it's got an orbital period of, I think, about 89 days. So these are fundamentally different than the planets that we're familiar with. And a big open question was, where are all the other Earths? We weren't finding any Earth-sized planets in year-long orbits. And the answer to that is we don't actually know because we don't have the technology or the missions to find them. So Kepler was designed to be the first exoplanet finding mission with the capability to find other Earths. And in doing so, it did completely revolutionize how we saw exoplanet science, because before we had about 90% of all the planets were all bigger than Neptune, and now we think about 90% of all planets are smaller than Neptune. So it just completely turned the world on its head in terms of exoplanet science, and we now believe that other Earths are some of the most common planets that we might be able to find.
Now, I know I'm speaking with a young person because I'm nearing 50 myself, 49 very soon. So this is a mission started in 2009. It's the Kepler Space Telescope, but it lasted a few years, right? About 4 years.
About 4 years.
And there was some failures on the kind of equipment side of things. Is that right?
Right. So essentially it has these 4 little what are called reaction wheels that are what control the telescope's pointing so that it can always look at the same section of the sky to look for exoplanets. And then one of them unfortunately broke. A second one broke not long after, and you need at least 3 to really be able to point stably. So the mission ended early. It was actually supposed to last for several more years. But even with the 4 years of data we have now, people are still finding new things in that, and it's been an incredibly valuable resource.
Now, I have a guest here in the studio. His name is Isa. He's come from Whistler Secondary School. He's missing school to be here in the studio, and he's signaling me to ask a question. But I will just say something. This is a man that was born in 2009.
Yeah, so my question is just, did it stay in like Earth's orbit while it was studying the stars, or did it go like somewhere else farther?
Great question. So Kepler was launched into what we call an Earth trailing orbit. So what that means, it was basically launched just behind the Earth. So Earth orbits around the sun every 365 days, and Kepler, I believe the period of Kepler was like 375 days. So it was really, really close to the Earth. It's kind of always following Earth. It is still there. It hasn't been, gone on anywhere else. It is officially shut down. It was officially shut down a few years ago, but it is still in an Earth-trailing orbit.
And you've said that the Kepler telescope was had a high precision, so it took really good quality photos, unlike what we'll talk about TESS, which is a little bit different, which is more on quantity. But let's stick with Kepler a bit, because Kepler not only monitored roughly, was it 150,000
That's
stars,
correct, yeah.
right? So, tiny changes in brightness every 30 minutes over those 4 years. But what it has, it's revolutionary. We went from, if I'm not mistaken, from just a few exoplanets, and then Kepler comes, and now we're in the thousands. Yes. And 4 of which, when you were doing your undergrad, you had discovered. And then, of course, during your PhD, many more as well, that were potential candidates, and as well as, probably confirmed, I'm sure. We'll talk about that process. But certainly an extraordinary mission, in your opinion.
Yeah, absolutely. Overall, it's found 4,700 planets and planet candidates. Planets being things that we believe they're confirmed planets. Candidate planets are those that we think have a very high likelihood of being planets, but there might be something about them that we're still not completely sure. We can rule out something else, like maybe it's caused by a star, or just the star itself getting variable randomly. So I think Kepler's confirmed over 2,000 planets at this point, which is about a third of all of the planets that have been confirmed from every mission across all 30 years of searching.
So even though more than a decade has passed, what the legacy of Kepler is still very much important, especially to your research, as I understand. So the incredible archive that Kepler has given scientists like you is still being used and reevaluated and understood, and even being poked at constantly. So it is, without doubt, was a really extraordinary thing. But now let's talk about something that you that you work a lot in. It's something called demographics. It's, I believe, an attempt to understand planetary populations statistically. But let's bring this word of demographics into the sort of astronomy world. What does it actually mean?
Right. So demographics is basically a population study, very much like how you can do a demographic study of people. Like, let's say you're testing how often people of different races or sexes or education levels, and any different dimension, you can kind of see how that changes over time in a various city. So what I'm doing is doing a population study to understand how common different types of planets are in our galaxy. And one of the things that we can do most simply is just simply look at the total number of planets we found so far. And we'll notice we have a lot of really big planets, we have a lot of small planets, but it's not as simple as just saying, 50% of planets are bigger than Jupiter, therefore 50% of planets are bigger than Jupiter in our galaxy, because some planets are a lot easier to find than others, which means they'll be overrepresented in our data set. Like an analogy would be, if you go to, let's say, a sports game and you ask, are you a sports fan? You're going to have a lot of people say, yes, I am, but that's an overrepresentation in your population. So you have to be really careful about thinking what types of planets are easier to find than others, and how might that affect our understanding of the underlying planet population. So a lot of what I do with the statistics is try to understand those biases, would be the word, and kind of understand what planets actually look like in our galaxy.
And biases is really the word, because it's this idea in your work that exoplanet data sets, right, are intrinsically biased based on even kind of the example you gave. And so we don't really simply, like the instruments and methods that are able to detect still pose a kind of problem in the demographics, right? Because you're still relying on those instruments, and of course you're trying to piece it all together. And then can you kind of get into the kind of biases that are really specific to, say, what you found in the Kepler data set?
Sure. So to understand biases, we first have to understand how do we actually find exoplanets with something like the Kepler telescope. So what Kepler did is what is called the transit method. And this is actually the method that I continue to use even at UBC to find exoplanets. And the idea behind the transit method is as you're looking at a star, if there's a planet in orbit around that star and that planet happens to pass directly in front of the star as it orbits, some of the light will get blocked from reaching us. So if we're measuring the star's brightness over time, we'll see just for a few hours, the brightness of that star will decrease because something is simply blocking the light. So you can imagine that the shorter the period, so the smaller the orbit of a planet, the more frequently these dips are going to happen. And they're going to be really easy to spot. Whereas something like the Earth, it's only going to transit once every year. So it's going to be a lot harder to see that than something like a 3-day planet. A bigger planet is going to block a lot of light, whereas a tiny planet like the Earth will block only a little bit of light. And so big planets are going to be a lot easier to see. So essentially the transit method and Kepler and other missions like TESS are biased because it's way easier to see these really big planets in really short period orbits than the really tiny long period planets like our Earth.
And they're called often hot Jupiters.
Exactly, yeah, the hot Jupiters. So those are kind of some of the earliest classes of planets we found just because they're so easy to find compared to small ones like the Earth. And yeah, they're fascinating because when you look at our solar system, all of the giants are super far away, and we designed all of our planet formation theories off of that configuration, and then suddenly these planets show up, and we didn't even think that they could possibly exist. And even today, we still have open questions about how they formed.
Now, when you were undergoing, and I hesitate to use the word planet hunter because that's often associated with your research. I mean, it is a kind of hunting, but I like to say explorer, like you're exploring new things. And one thing that I learned was that even in this using the transit method and this kind of detection, sometimes asteroids would get in the way and they could give you these false positives of like whether a planet was a planet, but, the asteroid would come in that. Can you give us a picture of what that actually might even look like?
Right. So different detection methods have different kind of false positives, so just things that mimic the side of a planet but aren't actually a planet. For the transit method, probably the most problematic one is that it's not actually a planet, but it's another star entirely. So if a star is passing in front of the target you're looking at, it will block some of the star's light and cause something that might look a lot like a planet transit. So that's kind of an example. As I mentioned before about how stars are just intrinsically variable, that means that they naturally get brighter or fainter with time. And so if this happens periodically, it could look a lot like a transit, just causing the star to get fainter every now and then. The asteroids are an issue for a different method called microlensing, which I've also used for my work.
And then there's also other things, right? Cosmic rays and other stellar activity that could affect this type of being able to distinguish between a real planet and everything else. So I want to get into now something that is really quite interesting because you have this distinction between a planet candidate and an actually confirmed exoplanet. So I can imagine there's a whole process that is beyond even what maybe you might even do. That could be with a group of other people that are now trying to make the confirmation. Can you kind of get into how that actually works? So, someone like you finds an exoplanet and what happens after that and how does it actually get confirmed as, yes, this is definitely one?
Yeah, so there's a few ways you can do this, but for transiting planets, kind of the most powerful way is to follow it up with a different technique called radial velocity follow-up. And what this technique gives you is essentially the mass of the object that's causing these transits. So if you have a radius from the transit method, right, you can measure the radius of the object because of how much light is being blocked. Especially once you get to something about 8 times the size of the Earth, that's the regime where it could be a planet, a gas giant planet, or it could be a brown dwarf, or it could be a low-mass star. They all have the same radius, but they'll have very, very different masses. And so if we measured the mass with the radial velocity method and we find that it's planetary, we can confirm it as a real planet.
And yeah, I just want to ask because obviously I was pretty young like when I was just born when the Kepler thing launched, but I do remember I think it was either like Kepler 29 or Kepler 22b got very like famous online for being considered like to have like certain life, and I remember it was disproven that they found something that didn't allow, like it wasn't similar to our Earth. I don't know if you know anything about it. I just remember it got very like personified online, and I kind of got mixed up that it wasn't really that much of, but it was more like a false promise.
I can't say I remember the story of Kepler 29
Or was Kepler 22b?
explicitly. So probably the planet from Kepler that looks the most like the Earth in terms of its basic properties is Kepler 452b. This is a planet that's about 10% larger than the size of Earth. It orbits a star that is the exact same type of star as our Sun, a G2 dwarf star, and its orbit is 385 days instead of the Earth's 365. So based off of all these basic properties, we consider it part of landing in the star's habitable zone. So this is the range of distances from a star where a planet could potentially support liquid water on its surface. It's just the right temperature for liquid water, which we obviously think is really important for life on Earth. But you did touch on kind of how there was some controversy. So this particular object was reanalyzed later after Kepler had kind of considered it a confirmed planet. And astronomers were worried that the transits were not actually caused by any other astrophysical object, but rather were just noise in the data. So one of the issues with finding these really tiny planets is that their transit depths are so small, it can be really hard to pick them out compared to other events in the light curve. And this was a case where people kind of have cast doubt on it being an actual planet. So even today, I think we still consider it part of our confirmed planets. If you look at the total number of about 6,300 planets at this point, it is still listed there. But it kind of gets into the challenge of being able to be so certain when you're looking for these and trying to confirm them.
And so when does the rubber stamp actually happen? And that, the names of planets are interesting to someone like me who grew up with very concrete names of planets. And they're in the thousands, and they're named by, what is the rhyme and reason for the naming? And then when do they get that rubber stamp? I'm just curious. Like, is there,
to the table.
When do they add to the table, and when is it official? And also I learned from you that a lot of this research is kind of in real time in a way that we, even as the public, can access what is kind of going on in real time, which is really cool. It's very different than before. So we can partake in I guess, that announcement of the one planet that might be now official in some ways, right?
Right. So basically it's the rubber stamp approval is somebody writes a paper that goes through peer review, and the referee for your paper reviews it and says, yes, you've given a convincing enough argument to say that this is a confirmed planet. And once it's in the published domain, then the NASA Exoplanet Archive has people that are scouring publications all day and add it as soon as they see a new paper has announced a discovery. So that's pretty much how these planets get added. The names of the planets are based off of the star that they were observed around, and then they get a little letter right after to indicate which order the planet was discovered in. So for Kepler 452b, that's an example of a planet that was found around the star Kepler 452, and the B indicates it was the first planet. In the case of multiple planets, we try to list them by increasing orbital distance. So B would be the innermost planet, C would be the second planet, D, etc. Although sometimes we might find a planet, let's say we call this one Kepler 76b, and then we find another planet that's even inner to that one, right? Now the letters are all mixed up. We don't rename them. We just kind of live with the fact that the names are a little bit chaotic. But essentially, we just do the best we can. Yeah.
That's great. And so in timeline, when would it finally be? It really depends on many variables. And how many people are working on that kind of confirmation? I'm just, once the paper that you said, that's a research paper that's published in maybe a journal. But how long are we looking at?
It's not uncommon for these papers to have 60 people on them.
Wow.
It's a lot of people, because let's go back to what the confirmation we kind of established. We want to measure the mass of this planet, which means we need to get data using the radial velocity technique. Now, in order to write a telescope proposal to do that, we need to have enough evidence beforehand, before we ask for that final step of the confirmation process, to make sure that we've ruled out everything else possible. So, for example, when we're finding a planet around a star, there's a chance that it doesn't even orbit the star that we expect. It's on a nearby star that was close enough that when we were measuring the brightness of its star, it basically was contaminating the measurements that we were making. And so one of the very first steps is to just confirm, do we see this planet transiting the star that we expect, or is it on something else? There's some stars are not amenable to doing radial velocity follow-up. They might be, there might be some issues with them, like maybe they're in a binary star system. There's a lot of reasons. So we typically do some quick, what's called reconnaissance, to make sure that the star is even ready to propose this data. And so as soon as you're getting, one person has to write the proposal, one person is taking the observations, a whole team is analyzing the data. You have all these teams internationally working together to do this. And so it ends up being about, 60 people on average. That's my anecdotal experience from writing several of these papers at this point.
That's amazing. And it's amazing that it is such, the ecosystem of that kind of collaboration is real, and it goes around the world, and there are no borders, which I think is really cool. I want to talk about TESS, because TESS is on right now as we speak, but let's just, and TESS, you can define again, but let's just take a little diversion, because this was very interesting to me, how your research is, yes, it's about, this looking at these massive databases and understanding, how all the things that you do in relation to exoplanets and their conformations, and how you can even sift them through all this mass information that you have. But there's also this other side that's really cool, where you're also understanding how planets form, how they migrate, how they lose atmospheres, how they evolve over time. So how much can astronomers actually infer about planetary evolution from this type of population level data?
Yeah, that's a great question, and it's one of the things that fascinates me so much about doing demographics, because what we can do is look at the properties of the planets that we see. We can see how that maybe changes with time. So we can compare populations of young planets versus old planets, and if we see there's a significant difference, then that means there's some kind of evolutionary process that is causing these changes. And then there's typically a lot of collaboration between observers like myself, who are taking these observations, finding planets, understanding their properties, and then theorists who come up with the theories to explain why we see all of these trends. And typically we try to collaborate so that if the theorists come up with an explanation, either from the planet formation stage or subsequent evolution, that can explain our trends, we might be able to test those theories with the observations.
That's fascinating. And then you are teetering on even other areas of research that are beyond, the physics and astronomy department. It feels like that to me, at least from an evolutionary side of things, right? Because you're entering other worlds in some way by getting this data. But let's talk about TESS, the Transiting Exoplanet Survey Satellite. It was launched in 2018, and its approaches to exoplanet detection differ than Kepler. Kepler emphasized, as I mentioned earlier, that kind of precision and depth, and then it looks like TESS really is about scale and surveying enormous regions of the sky and observing millions of stars. What can you tell us about TESS? Because you had a relationship with it at MIT.
Yeah, so I worked on the TESS mission as a postdoctoral associate and then later as a postdoctoral fellow. And this was what I worked on right out of my PhD at UBC. So for my PhD, I had focused on finding new planet candidates with the Kepler mission, and TESS was hiring for someone with exactly my skill sets to basically do the same thing with TESS, and I was very excited. So The TESS mission is based out of MIT. That's where the principal investigator lives, and it collaborates. It's a NASA mission, a NASA-funded mission. So I worked with a lot of MIT researchers as well as NASA researchers on this mission. So TESS, as you mentioned, it kind of took a very different approach to planet finding. Kepler was really interested in pinning down the demographics of small planets. So that's why it had to look for so long, right? It looked for 4 years at the exact same stars to try to see just a few transits from Earth-sized objects, in year-long orbits. Whereas TESS was much more about, let's do an all-sky survey. Let's survey all the nearest and brightest stars. And the reason for that choice was because it's the nearest and brightest stars that are most amenable to that radial velocity follow-up. So a lot of the Kepler stars are very faint. We're never actually going to be able to measure a mass for a lot of these planets and therefore confirm them. Whereas TESS, by searching for planets around really bright stars, they're a lot easier to follow up and confirm and potentially follow them up with things like the James Webb Space Telescope to do atmospheric characterization and all sorts of other science.
And I can't help myself with jumping right into the idea of rogue planets, because that's something very TESS, if I'm not mistaken, at least in some of the things that have come out through TESS.
So I believe my team is the only people in the world who have actually done a rogue planet search with TESS. It's not a very it's a very new idea because TESS was never designed to search for rogue planets. But there's going to be a mission launching later this year, the NASA Nancy Grace Roman Telescope. It's the next flagship mission out of NASA, and searching for rogue planets is going to be a really big goal of that. And so I had an idea with a few collaborators a few years ago to use TESS as like a precursor to Roman to understand how to design rogue planet searches with space-based telescopes.
Now, you got to define what rogue planets are, because I was very excited when I was listening to you talk about rogue planets in one of your lectures and what the implication of them is. And there's an acronym too, FFP.
Yeah. So rogue planets are also called free-floating planets, and those are those planets that don't orbit any star that I mentioned earlier. So depending on your definition of exoplanet, they are not exoplanets because they don't orbit another star. I personally consider them exoplanets, but not everybody agrees. So there's kinds of two...
Can I stop you there?
Sure.
Why do you consider them exoplanets?
Because their origins are probably consistent with having been exoplanets at one point. So they're kind of these two major origin scenarios for how rogue planets can exist. And one of them is that they originated in a planetary system like other exoplanets, like our own system. But then in the early days of planet formation, it was much more chaotic. You had planets crashing into each other, you had them scattering, you had all sorts of things, and they might have been ejected from their system, and so that they're now no longer gravitationally bound to any star. So because they were at some point an exoplanet, I don't know, I feel like...
You're acknowledging what you believe is their origin.
Yeah, but then there's another class of these rogue planets that might have... some of the bigger ones might have just been something that was starting to form into a star but never got quite massive enough to reach the phase of nuclear fusion. So it just was kind of like a failed star, so it remains this planetary mass object. So in that respect, I kind of see not calling that an exoplanet, but just as long as it's a planetary mass object, I consider it an exoplanet. Okay,
so go back to where you were. So they're free floating. They're not orbiting any star. They're quite unique. And this is like a byproduct. This is not what the TESS mission, as you said, was intended to find. However, this is something that you have a vested interest in. And so what do you envision and what do you imagine that you're going to find as you keep investigating this more?
Yeah, I'm pursuing this with one of my students right now, so I'm really excited about it. So the idea behind the search in the first place was TESS is not designed to find these types of objects. It's designed to find transiting exoplanets, right, with the transit method. But you can find rogue planets using the same data set, but a different technique. So this is a technique called microlensing. It's unfortunately one of the harder methods to explain because it involves general relativity. I guess like an analogy I can give is imagine you're looking at a really far away light bulb, and somebody holds a magnifying glass and passes it between you and the light bulb. And as soon as that magnifying glass lines up just right, the light from that light bulb in the distance is going to get brighter, right? Because you've got a magnifying glass in front of it, and then it'll end, that brightening effect will end as the magnifying glass continues on its way. So in this sense, that background light bulb is a background star, just in the background. The light bulb is the rogue planet passing in front of that distant background, and the magnifying effect is caused by the planet's gravity bending light around it. And so we have this what's called a lensing effect, where the light from that background star will temporarily be increased multiple times. So we can use the same data sets that are measuring brightness over time, right? But instead of looking for these periodic decreases of brightness, we're looking for these one-time increases of brightness. So the idea was, TESS is taking data every 200 seconds, and some of these events caused by like a terrestrial mass free-floating planet might only last for an hour or so. So we have enough data over a given hour to see these events happen. And because TESS is looking at 1 million stars every month, these are extremely low probability events to have such an alignment that this effect happens. And so you need to look at a lot of stars. And so because TESS is doing this for, 1 million stars, hundreds of millions of stars over the whole TESS mission, surely this will have happened at least once. So we did some predictions, and we found that there have only been 3 free-floating planets of terrestrial mass ever discovered across decades of searching, and so we really don't know how common they are. And so depending on how common they are, maybe we would expect 1 detection, maybe we would expect 20 detections, maybe we would expect to see nothing. But at least if we try to search, we could maybe constrain that a little bit better. So what happened is we picked just a random month of test data. It was completely arbitrary choice about which data set to use, which subset. And this was about 1 million stars in this data set, and we searched it, and we found something that looks like the lensing event from a free-floating terrestrial mass planet in our very first sector. So there's a few explanations for this. Either rogue planets are significantly more common than anybody would have expected. Either we were extremely lucky to have found this, or it's not a rogue planet. It's something else. So there are, just like how the transit method has false positives, the microlensing method does too. Asteroids crossing the field, right? Light from the sun will bounce off the asteroid into the telescope and cause a brightening event. But what the microlensing community seemed to be most concerned about was that this is a flare. So stars are magnetically active, and our sun goes through these cycles, and sometimes it's more active than not. We just got through a really big peak in magnetic activity from the sun, which is why we had all those aurora borealis that you could see, right? That was basically caused by a flare from our sun, and all this solar wind, hitting the Earth's atmosphere and causing these auroras. So this is basically a one-time increase in the brightness of the star that might look like a microlensing event. These flare events are usually very asymmetric. They'll have like a really quick increase followed by a very gradual decay, whereas microlensing events are very nice and symmetric. So we initially didn't think that this was a false positive. But when we posted our paper online for other people to read, that was what the microlensing community were most concerned by. They're like, well, but what's interesting is that before our paper, these had never been considered as a false positive. And I talked to one of the lead mission scientists for the Roman missions, a microlensing search, and he said, yeah, the paper that you posted, like this event, the fact that you found it is causing everybody to rethink how to do microlensing searches. And
that's got to make you feel a sense of satisfaction and just thrill. It's pretty cool.
Yeah,
this is groundbreaking.
I'd like to think so. I think it's just because it's an event that has confused a lot of people. Like, I cannot say that it is a rogue planet. I also can't say it's a false positive. We don't know. And so some people are totally adamant, like, no, it's not a rogue planet at all. And we've had a lot of responses from both sides that have been both positive and negative.
But the thing is that the idea exists, and that is exciting. That is really novel, and that has to keep you coming back to the office, just because that is something you really want to get after. That.
Yeah, so I have one of my undergrads actually is going to continue the search and do it for the full TESS data set. So I mentioned that this was based off of a search of a single month. We then searched another 5 months and didn't find anything. Yeah. So maybe we really were just lucky. But now we're going to do all roughly 90 months of data that we have. So we have potentially a lot more of these events to find. And if it turns out that this still remains the only possible free-floating planet, then that actually makes it more likely that it's a real rogue planet, because it matches our predictions for the number of detections over the full TESS data set.
And for rogue planets, do they just drift with the expansion of space, or do some of them? Because you said how you think some of them are formed as from other planets hitting, and I know there's nothing to, slow anything down in space. Would some of them still be moving, or do they just drift with the expansion of space?
So they would all still have some velocity from their initial ejection, and some of them might even be captured eventually by other systems. So how do we, when we find a transiting exoplanet, for example, there's a chance that this never even originated from the system that we're observing. It was captured at some point. So we're not going to be able to tell that answer from the planets we see, but what people have done is simulated how often do we think these objects are being ejected. If we model the early solar system, do we think that this was a common process, that this was a rare process? What are the typical size distributions of objects that are getting ejected? And we actually predict that free-floating planets outpopulate our bound planets by about 10 to 1. So there's rogue planets everywhere, floating around. Yeah.
And also, and I know it's not that uncommon for other things to go into another solar system. I know, I think it's Oumuamua. I don't know how to say it, but I know that was the first thing we discovered that was from another solar system that reached ours.
So there was Oumuamua was the first interstellar object. Came through our solar system in 2017. There was 2I Borisov. I think I might want to double check the name later. And then the one that was most recent in the last year was 3I Atlas. So we've had 3 interstellar visitors so far. They're all probably comets that were ejected from their original systems that have come through now. But of course, those are the only ones we've detected. For all we know, there are several more that have passed through the solar system, and we just didn't have the images at the time to be able to see them. But we think that this ejection process is really common, especially for small objects, and that's why we think these terrestrial mass free-floating planets are probably dominantly caused by this process.
That is just absolutely fascinating. And this Roman Space Telescope is going to be launched very soon.
On my birthday.
Amazing.
Yeah, it's as always with these big missions, they might get delayed. They have a projected launch date of September 7th of this year. So that would be a great birthday present if it launches and it works perfectly and everything goes smoothly. Obviously, that might get delayed, but yeah, it'll be very soon.
That's really exciting. Now, I want to talk about the idea of finding planets that are similar to ours, where, that are habitable. But before I do that, could you quickly just tell us, because, and for those of you who've just joined us, I'm speaking with Dr. Michelle Kunimoto. This is an extraordinary interview about the research that Michelle does with her team, and also what we can really understand about exoplanets. So beyond our solar system, planets that we may never see in our lifetimes, but certainly are there in our imagination and through a lot of data that scientists like Michelle are looking at on a daily basis. And this is, you're tuned into the Blue Hour on CiTR 101.9 FM and also streamed live on CiTR.ca. But before Michelle, I want to talk about Earth-like planets, and that big question of are we alone, which everyone wants to ask people like you. But there is a few things that UBC does here. A UBC-led TESS faint star search that you are, really a big part of, and you're hoping to attract more students and scientists like yourself. And as well, something about that is really cool called LEO, Lazy Exoplanet Operations. This is a way to distinguish planets from some of this kind of noise out in that world and stellar variability, etc. So if you could just quickly touch on that, and then we'll dive in from what we were talking about, rogue planets, right into something that NASA has come together, I believe, in 2010 to look at 2020 to look at what is really the next thing that all astronomers should be doing.
The decadal survey, yeah.
Yes, and that's every 10 years, and it is the amazing observatory that's going to be called the
Habitable Worlds Observatory.
Yeah. So first, what's that here locally, and then we'll dive into that.
Yeah. So when I worked on the TESS mission, I was the lead of MIT's Planet Search team. So this was called the Quick Look Pipeline, and the QLP's job was basically to take all million stars that TESS observed every month, make light curves, those measurements of brightness over time, and then search for those transiting exoplanets using various algorithms to make it automated, because we can't manually go through a million objects, right? But the resources that are needed to do such a big search, to search a million stars in a given month, and you have to be finished before the next month's data becomes available. Essentially, we didn't have the algorithms that could do this completely automated, and so we had to restrict ourselves to only about 10% of that sample. So we made light curves for everything, but we only searched about 100,000 stars. So as part of my kind of postdoc project, I was thinking, well, I just finished my PhD at UBC. I designed planet search pipelines. I designed practices to make this very automated. So what if I take kind of the tools that I developed as a PhD student and make this a more automated process? So that turned into what you just mentioned, the faint star search. Essentially, those 100,000 stars that TESS looked at, that QLP looked at, were all the brightest stuff, like the highest priority stuff. But that left 90% of the stars not looked at for planets. So the fainter stuff. So I basically designed a bunch of new code bases, ran my planet search on this, and out of the roughly 8,000 TESS planet candidates that have been found so far, that has found about half of them. So 4,000, I think we're almost to 4,000, and this is something that I continue to lead out of UBC, and I continue to collaborate a lot with the TESS team to make sure that my candidates are alerted as official TESS objects of interest so that other people around the world can start following them up, potentially confirming them. But yeah, as compared to all the other search teams out of MIT and NASA, this is actually the most successful in terms of number of candidate detections.
So faint star search, what a great, description. That's what you're doing.
Yeah, it's pretty straightforward. So as part of the faint star search, right, we have to try to automate the process of finding planets. And one of the most important things in this process is once we find a potential transiting periodic signal, we have to distinguish it from planets, from brown dwarfs, from stars, from stellar activity, right? That's where LeoVetter comes in. Mm-hmm. So LeoVetter was my answer to this whole problem of how to automate this process. It's essentially it does what's called vetting. So it takes a planet candidate signal that we see in the light curve, and then it runs a bunch of tests on it, and then it tells me if it's most likely a planet or some false positive. I came up with the name because Leo is the name of the sports mascot for my favorite sports team, the BC Lions, Leo the Lion. And so I came up with what the L, the E, and the O stand for after I came up with the name. So Lazy Exoplanet Operations. We love our acronyms in astronomy. So LeoVetter is a publicly available code base. It's on my GitHub. Anybody can download it and use it for their own planet searches. And I published a paper on it last year, and I know that there are several teams around the world who are already using it. So it's been very exciting collaborating with them and hearing that it's been useful for the TESS community.
Amazing. And we are getting so close to the end of our talk together, but let's really dive in. Oh, there's a question. Yes?
Okay, I just wanted to ask, like, and if any of the most of the exoplanets that we've discovered, can you see their like stars or their systems with the naked eye? Because I go stargazing a lot, and obviously, I don't find exoplanets like you. I just look at constellations, but I'm just wondering if any of them that have been discovered or are notable or similar to Earth, can you see them with the naked eye, or are they mostly only seen with like telescope?
Most of the planets we found would be only accessible with the telescope, but there are a lot that you can see from the naked eye. In fact, a lot of the planets that have been found around stars observed with the radial velocity technique, those are going to be really bright nearby stars. You can definitely see those with your own eyes. Obviously, you wouldn't be able to see the planet because it's so tiny and faint compared to its star, but yeah, the stars that you see will have exoplanets around them.
And my other question is, I don't know if you're familiar with it's called Space Engine. It's like a game, and it has like the entire universe. And I searched up one of the exoplanets you found, and they had it in there.
Oh, that's hilarious!
Because they have like it's like it was developed by an astronomer, and it just like has like theoretically the full universe. It's mostly like procedurally generated, but you can search for planets, and I went to Google and I looked up the ones that you discovered, and one of them was there.
Thanks for telling me that. I'm also a really big fan of the Mass Effect series from BioWare, and they made some remastered kind of legacy edition, more recently, and you can see this galaxy map of various famous planetary systems that have been discovered, and they added a lot of the ones from Kepler. So they're clearly some very big science fans on the development team for Mass Effect.
Yeah.
So finally, that a little bit of an answer to this burning question: if we find an exoplanet that is habitable, that we can live on one day in our future, I mean, that is on the minds of many astronomers around the world, and that's why this incredible observatory is in the works. That has been maybe 2040s potentially, but of course, in order to justify the costs of making that observatory, this data that you're working through, all of the things that you are with your team are finding is really important in this next step. And can you talk briefly about that? And I really have to ask you, like, do you dream about, does this kind of stuff go into your dreams in a sense that you can imagine these other worlds, just because you're lucky to know more about them than just an average person?
Right. So I'll answer the first question first. So the Habitable Worlds Observatory, as you said, it'll hopefully be launching in the 2040s, and so we're currently, we as in the astronomical community, are currently in the mission design phase. And one of the most important questions is to say, how big of a telescope do we actually need? Because the purpose of this telescope, or one of the main purposes, is going to be to directly image other Earths around other suns. So currently, a lot of the methods I've talked about, like the transit method, radial velocity, microlensing, they're all indirect methods of detection. We're not seeing the planet itself, but direct imaging is literally taking a picture of a star, trying to block out the light from that star as much as possible, so that you can see the fainter objects like planets orbiting around it, and literally taking a picture of another exoplanet. So we have been able to do this for really, really big planets that are really far from their stars. But we've never been able to do this for something that looks like our solar system, to the relatively close in Earth-like planets. So the Habitable Worlds Observatory will be the first telescope capable of doing this. But in order to design that, we need to know how common other Earths are in our galaxy. Because if they're all over the place, then we can pretty much pick any star that looks like our sun, observe it, and we should be able to see an Earth-like planet. But if they're really rare, we have to think a lot more carefully about how many stars do we want to follow up? Which ones are the most likely to host a potentially habitable planet? And so one of the research projects that I've worked on in collaboration with NASA is to answer how common are other Earth-like planets. The planets that fit the basic properties of another Earth. They're similar size, similar orbital period, orbit around a similar type of star. And our answer is there's a lot of uncertainty. Kepler, because it ended early because of those instrumental failures, it wasn't really able to give us the constraints that we would have hoped for. But we estimate around half, so 50% of all sun-like stars probably have another Earth-like exoplanet. So if there's hundreds of billions of sun-like stars in our galaxy, that could mean hundreds of billions of potentially habitable Earths. But again, depending on what that number actually is, that's going to be really important for defining the size of the telescope that you need.
And most of them that they're like super Earths or sub-Neptunes, right? Isn't that like the most common?
That's correct. So planets between the sizes of the Earth and Neptune are the most common planets we found so far, and we don't have one in our solar system. So that's an open question.
Yeah.
This has been extraordinary, and I didn't even get into some of that juicy stuff. But you know what? Dr. Michelle Kunimoto is no stranger. You can Google Michelle Kunimoto, and you will find plenty of interviews and videos, and definitely diving into, what really is the beginning of your journey from a very young age, from being at, what I called growing up in Vancouver as the planetarium, and being connected with a community young, having a telescope in your hands very young as well. And that inquiry and that curiosity has led you to what I really believe you are doing now. And I feel that this conversation has been very Galilean. I don't know if that is the right word, but what it means to me and what makes me so inspired by people like you, Michelle, and I say this sincerely, is that what you and your team are doing is extraordinary. This is, as I said earlier, in real time, this is extraordinary work that is changing, evolving, and transforming the narrative. And it's a collaboration, but it's also, there's discourse. It's got everything. And I think that's what the cosmos is. It's a place of chaos as well as a place of beauty and harmony. And all we need to do is go out. And Jamie Matthews is going to be on the show next week. He was a guest on what used to be called Prof Talk before the Blue Hour many, many years ago. And he's a mentor to you in a big way. And we'll talk about you, I'm sure, when I talk with Jamie next week. But I'm going to end it there. Thank you so much for coming and sharing your enthusiasm. And we will be following you. And I think you're going to have to come back because your research is so fast paced and so many cool things can happen. We need you back, and you got to give us an update.
Sounds good. Thank you so much.
Yeah, I hope you enjoyed this.
Really did.
Thank you.
Thank you.
And thank you, Isa, for joining in. So that is the Blue Hour on CiTR 101.9 FM. And this show will be podcasted on CiTR.ca. And then I'm going to have a partial transcript. I'm not going to delete a lot because there was some really good pieces in that interview. So it will be on the hourisblue.com. So it's just a reversal. But the hourisblue.com will have a podcast link as well, and as well as a transcript that I hope Michelle can share as well. Thank you. Thanks again.